right, let's get started today. Today we're going to continue on transonic, compressible aerodynamics, and shockwaves. All right. So this is something we ended up in the last lecture's discussion. It looks complicated, but it is essentially saying that the ratio of how much flow you get per unit area, right? We looked at rho, right? The density is in the isotropically accelerating or decelerating flow is going to be proportional to 1 plus gamma minus 2 minus 1 over 2 times Mach number squared to the power of minus 1 over gamma minus 1, right? So this is from our previous derivation of how the pressure changes, right, as the flow accelerates or decelerates. That turns out to be the same thing to the power of minus gamma over gamma minus 1. And the density being being the pressure to the power of 1 over gamma turns out to be proportional to the same thing to the power of 1 over gamma minus 1. Okay, so since density goes like this, and the velocity is going to be the Mach number times the speed of sound, right, which turns out to be gamma times p over rho, and both p and rho can be written in this form. So that turns out to be the Mach number times 1 plus gamma minus 1 over 2 m squared of what we can is we take the square root, and a square root becomes half, right, in the exponent, and we have just p becomes the pressure is gamma minus 1, and the density is 1 over gamma minus 1. So that's what it turns out to be, and after you do the math, you're gonna find out the rho and u both can be written as something that is just a function of the Mach number, right? So essentially, rho times u is going to be proportional to some function of the Mach number, and when you push the flow through a nozzle or a duct where the area changes, then you're going to know that the rho u, the area has to be inversely proportional to rho u, right, the mass flow per unit area, and therefore that's going to be 1 minus this function. And I'm just writing down this function explicitly to let you see what this looks like. And unsurprisingly, the minimum area is at Mach equal to 1, right? So at the Mach number very small, we basically have a 1 over Mach number relationship for the area, right? Because density is going to be constant. But that 1 over Mach number relationship becomes more and more shallow, becomes shallower than 1 over Mach number as Mach number approaches 1, and it becomes a zero slope at m equal to 1. And above m equal to 1, the required area increases as you increase the speed instead of decreasing. Okay, so this actually comes back to our convergent divergent nozzle, right? So basically, in a convergent divergent nozzle, when you have all subsonic flow, when you have incompressible flow, of course we know that the velocity is inversely proportional to the area. But when you have all subsonic flow, the relation of how the pressure changes across this nozzle is very qualitatively similar to an incompressible flow, right? When you have a small area, we have a high Mach number, and as a result, a low pressure, okay? But the relationship breaks down when the throat reaches Mach 1. And what happens afterwards is going to be the subject of today's lecture, okay? Before we go to discuss shockwaves, which happens over here, let me just give you an example question that's related to this nozzle, actually at subsonic conditions. So that is, how do you calculate the thrust of a rocket? Okay, so let's say we have a we're testing like the nozzle geometry of something, and to test it, we have a large plenum filled with air of pressure P0 and the temperature T infinity, let's say, okay? And we let the air out of the nozzle, so the plenum over here is so large that we can assume that the velocity inside it is pretty much zero. All right. Now the question is, first of all, if we assume incompressible flow, how would you calculate the thrust? So here's the information we know. We know the geometry of the nozzle, so the throat is known, the exit area is known, and the plenum condition, P0 and T infinity, are known. All the other quantities are something we don't know. So how do you calculate the thrust? Right. So basically, we have this rod holding this whole thing at a steady state. The question is, yeah, if we put a load cell on the rod, how much force would we measure? Yes? We can just use density times area times air velocity at where? At the exit, right? So what principle are you using to assert that? Conservation of momentum, that's right. Okay, very good. So this is because the velocity over here is almost zero, and when you look at the region over here, you can pretty much say it's a steady state, right? Because the plenum is large, so that the rate of change of flow velocity as a function of time can be assumed to be small, right, if the plenum is large. So if you draw a whole control volume over here, right, you can look at what is the rate of change of the momentum inside it. Okay, so first of all, there is a rate of change, right, because the air over here is being bled out, but there is no velocity over here, right? So although the mass is decreasing over here, the momentum inside the plenum is not changing. All right, because it's zero anyway. And then the momentum in this nozzle area is also not changing because of steady state flow, right? So that means that overall rate of change of momentum inside it is almost zero. And then if you include the outside of this plenum in the control volume, then all the outside has pressure equal to ambient atmosphere pressure, right? So the pressure is also not doing any, not impacting any force. So the only thing that's going to change the total momentum in this control volume is, one is the force holding the rod, and two is the flux of momentum out of here, right? That's why the force holding the plenum should be equal to the momentum flux. All right. Now we know the principle, right? So the thrust should be equal to the density times velocity times area. Now, what do we know, what we don't know in this relation? The only thing we know is AE, right? We don't know rho, we don't know UE. Oh, well, okay, so we are saying incompressible flow. So yeah, we know that the rho out of here is equal to the rho inside of here, which can be calculated using P0 and T0, right? So rho can be easily calculated. How about UE? How do you calculate the exit velocity? Yeah.
Based on the pressure gradient?
Based on the pressure gradient, specifically, that's right, based on pressure, but specifically how?
Using the isotropic flow, like pressure ratio equation with the Mach number.
Yeah, so here it's actually simpler, right? We are saying, what if we have incompressible flow, right? What you said is a correct thing to use when we get to compressible flow. That's right. Is there something even simpler to use for incompressible flow? Oh, by the way, I should say like everything we are also assuming inviscid flow over for the entire problem. Yeah. Yeah. Use Bernoulli again, right? So basically, we know that if we follow a streamline that goes from the interior all the way to the exit, right? That's a streamline that actually, let's just don't start from all the way to from the interior. Let's start from a region where we can start to assume a steady state flow, right? Okay, and ends at the nozzle. So over here, if we can assume the whole streamline is incompressible and it's also steady state, then we can use Bernoulli, right? So inside of here, the velocity is equal to 0, and out of here, the velocity is UE. And inside of here, the pressure is P naught, and out of here, the pressure is P infinity, right? So we know that P naught plus half of rho 0 squared would be equal to P infinity plus half of rho UE squared. And since we know P0 and P infinity, sorry, I should say we also know P infinity, right? Then we would be able to calculate UE and plug it into here to calculate the thrust. All right? Yes?
Would that be rho UE squared AE momentum?
Oh, yes, sorry. That's right. We should have a very good point. The momentum is rho UE squared times AE. Rho UE is the mass flux, and that times another UE would be the momentum flux. Yeah, thank you. All right. Okay, any questions on this part before we get to the compressible question? Oh, we didn't answer this question. When would this assumption be valid, right? How do you assess if the thrust calculated in this way is going to be a valid number? Again, the quantities we know are the upstream conditions, the nozzle geometry, and the atmosphere pressure. Yes? Okay, so yeah, so the Mach number needs to be very low, right? So how do you calculate the Mach number? And specifically, we use the streamline from here to here, right? How do we know that the Mach number is small across the entire thing? Yeah?
You have to calculate the velocity at the throat.
Yes, you have to calculate the velocity at the throat, right? So this is actually the first half of the question, right? We can just use incompressible relationship, but the second part of the question, we have to actually use some knowledge from compressible flow, right? So now the question is, how do you calculate the Mach number at the throat? Well, actually, you may be able to get by saying if you just want the Mach number to be much less than 1, you can get by assuming everything is incompressible, calculate the velocity over here, right? By basically backing out if you have UE, then in incompressible settings, right? UE times AT divided by UE times AE divided by AT would be the velocity over here, right? And if that velocity, assuming the speed of sound is constant, right, which can be calculated from here, it's very small. You can say, okay, it's incompressible. So let's get to the compressible question. What if we have compressible but subsonic flow, right? How do we calculate the thrust in this setting? So let's come back to how we calculated the thrust in incompressible settings. First of all, the conservation of momentum is going to be actually exactly the same, right? Okay, and the momentum flux is still equal to rho times UE squared times AE, right? Okay, there is nothing changes about momentum flux or conservation of momentum. But the blue equation cannot be used anymore, right? And Again, AE is something we know, but rho is now something we don't know anymore. And UE cannot be calculated using that. So what do we do when there is compressible flow? Okay, so here, let me just tell you one very commonly used strategy for dealing with the compressible flow is to get the Mach number, and everything actually can work out back out from the Mach number. And specifically, it is most convenient to figure out what the Mach number is in a steady state flow, right? Take a frame of, I mean, in this case, it's trivial, right? But like in later, you're going to see that you want to take a frame of reference in which the flow is steady state and figure out the Mach number associated with that frame of reference. Okay, so in this case, let's start thinking about the Mach number sense, right? So inside the plenum, the Mach number is equal to 0, right? Okay, so that's the easiest thing to figure out. What is the next Mach number that can be figured out? If the whole flow is subsonic and inviscid, we can assume the whole thing is isentropic, right? So based on isentropic relationships, what is the easiest Mach number to figure out in the whole system? Yes? The Mach number at the throat. How do you figure that out?
Using the isentropic relations, you have to apply the choking constraint, because it could be like less than 1, but it can't be more.
Okay, so if you follow the choking constraint, right? So if you follow what I had in the last slide, what you get is the ratio between an area and a choking area, right? So that is basically for flow that chokes at a certain point where the flow is equal to the speed of sound. So that's going to be useful for figuring out when the flow would actually be subsonic or it is not going to be subsonic, right? But in this case, if the whole flow is subsonic, right, then it's not that useful to calculate a ratio of an area versus the choking, like the minimum area, where the speed of sound, where the flow is actually at Mach 1. So there is actually something else that can be used to calculate the Mach number at someplace else. Yes?
You can use P infinity over P0 to find the Mach number.
At where?
At the exit.
Yes. So the easiest Mach number to find out is actually the Mach number at the exit. And what you use is the ratio of pressure here versus pressure here, right? Because the flow from here along the blue streamline is isentropic, right? And at upstream, we have Mach number 0, P equal to P0, right? At downstream, we have an unknown Mach number and P infinity. So the ratio of P0 over P infinity is known. As a result, we can know that, okay, so P0 over P infinity has to be equal to 1 plus gamma minus 1 over 2 Mach exit squared to the power of, for pressure ratio, it's gamma over gamma minus 1, right? Okay, so here you figured out what is the Mach number at the exit. So as a result, once you figure out, you can solve for Mach number at the exit. Okay, once you have Mach number from the exit, what you get is you can know not only P0 over P infinity, you can also know rho 0 over rho exit, right? That's going to be a function of this Mach number exit again, but with the power of 1 over gamma minus 1. So from here, you can compute what is the density at the exit, and as a result, this part is now known, right? Good? But we still don't know UE, right? So how do we know UE? Well, we already have the Mach number, right? So from the Mach number, you can also calculate UE is equal to the Mach number times the speed of sound. Right now, we just know is gamma p over rho. So since we both know what is the exit pressure and exit density, right? So basically, the density and Mach number combines together to calculate what is the velocity at the exit. So this is the steps you take, right? So you figure out the Mach number, and you're going to discover once I know the Mach number, everything else is easy to calculate, right? So this is really the key step in this solving the problem. All right. Okay, questions? I mean, the algebra is always going to be a little bit complicated in compressible flow because of this thing over here, right? But like conceptually, it should be pretty clear what to do. All right, any questions on this? No? Good? Okay, so let's go into shock waves. What's actually happening when we have, when would this assumption be valid? When do we know that the flow is actually subsonic? Or when can we follow this to actually get what is the thrust, right? So once you have that, let me just write out the T is going to be rho E times UE times AE, right? Okay, so how do we know that this equation followed using these steps actually gives us the right answer? That at the throat, right? I mean, if you look at the entire process, we did not use the one of these givens. What is the area at the throat, right? Seems to be irrelevant, right? It is actually irrelevant to the thrust as long as the whole thing is subsonic, but it is relevant in determining whether or not the whole thing is subsonic. Okay, so how do we calculate whether the flow is subsonic or not? Yeah. Now we use the area ratio equation, right? Specifically, how do we use it?
If you use the area exit, and then we get like a ratio that means the area of the group is less than your sonic area, and it's like, it was supposed to, we thought it didn't.
That's right. So let's say so we figured out the Mach number at the exit, right? So let's say our Mach number exit is here, for example, like 0.3, for example. All right. Then from this plot or this equation, we can calculate that, okay, so the area ratio to a choking area is around 2, right? That means if the exit has a Mach number of about 0.3, then the throat cannot have an area that's less than half as big as the exit area. All right. What this means is that what means on this plot is that, okay, so if you are thinking about the acceleration process from the throat to the exit, the Mach number decreases along the process, right? If it's all subsonic flow, the area expands, the flow decreases, right? So as the Mach number decreases from somewhere on the throat to a Mach number of 0.3, the area should increase from this to this. So if the throat area is less than half as big as the exit area, this cannot happen, right? It's impossible for the flow to decelerate subsonically, isentropically from that throat area to a Mach 0.3. So that means the assumption we are making cannot be valid. The flow has to choke somewhere. All right. Okay, so this is going to be useful for determining if the flow has choked or not. And again, you need Mach numbers. So the first thing you really want to figure out for any problem like involving compressible flow is take a frame of reference where the flow is steady state and figure out as many Mach numbers as possible. All right. Okay, good. Okay, so shock waves. So again, like when we go back into the convergent divergent nozzle, right? And we have discussed all the way up to this point where the flow chokes, right? And at this point, we have said that, okay, even when there is an infinitesimal change of area, the changing Mach number is not going to be infinitesimal anymore. So instead of having a horizontal tangent line here, we get a sharp corner over here. And this is the minimum pressure at the exit you can ever get without having any supersonic flows. And when you further decrease the pressure, we get a line that starts like this. So we get supersonic flow, right, in this region. And unless to maintain like a supersonic flow all the way, we need a minimum pressure. We need actually a pressure as low as this. So there is a whole region in between where the flow in the expanding part of the nozzle is partly supersonic and partly subsonic. And the shock wave is the transition between a supersonic region back to subsonic regions. Okay, and let's actually use a very two examples. One example is on top of an airfoil. If you draw the streamlines, you're going to see that the streamlines actually resembles a convergent divergent nozzle very much. So, for example, if you look at a stagnation point streamline, goes like that, right, and follows the contour of the airfoil, and think about another streamline above it. So first of all, you get a converging section because the area decreases, right? The flow has to avoid the part of the airfoil. But as the flow go to the trailing edge, it has to expand again, right? And so you can imagine this is the throat, and then you have an expanding region. So when the flow is fast enough, the throat is going to choke at Mach 1. And after the throat, in the expanding region, there is first so this is Mach less than 1, and there is going to be first a region with Mach greater than 1, and then it encounters a shock wave where the flow transitions back to Mach less than 1, right? So that's what happens on wings. That's very much similar to basically many convergent divergent nozzles. All right, okay. Another thing I want to show you of what a shock wave is actually in the microscopic scale is the what happens with cars on the freeway. So it turns out you can derive very similar equations that solves for not the conservation of mass and momentum of airs, but the conservation of mass, well, not mass, but number of cars and the momentum of the cars, like on freeways. And you can actually observe what's happening on freeways, and that's actually very analogous to how shock waves are happening in air. So watch this region where the cars start to slow down, and watch the boundary between slowed down cars and the cars are still moving. Look at here. All right, you want to watch again? This is might be very hard to see. Right, watch these cars. All right, okay. So what you're seeing is that let me actually maybe let me slow it down a little bit so that like it's easier to see. Playback speed. Let's make it very slow. Okay, so here you can see the slowdown is already happening over here, right? The cars are very close to each other, which means the density is high, right? Okay, and so the density is high, the velocity is low, and over here upstream the velocity is still pretty high and the density is low, and then there is going to be a propagation of the shock front. Right, look at the boundary between the high density cars and low density cars. It's now over here, it's now over here, it's now over here, right? It's now over here. So this is like the shock front. This is the shock front. And the cars are like air molecules, right? The shock is now over here, and propagated all the way upstream.
I like the other side better.
All right. So yeah, so basically the shock wave is like the boundary between a high density region and low density region of the flow. And in our analysis, we'll be taking a frame of reference, not stationary to the highway, also not stationary to the cars. We are going to actually take a frame of reference that's stationary relative to this shock front and do analysis over here, right? Because if we take a frame of reference that actually moves with the front of the shock, we can actually do steady state analysis, and that makes our life a lot easier. Okay, so let's actually start to look at what happens across a shock. And we'll first look qualitatively and then look quantitatively. So here we have the shock sitting here, and we have supersonic, just to say Mach greater than 1 over here, and after the shock we have Mach less than 1, still going to the right. Okay, so let's first qualitatively look at how the velocity, the density, and the pressure are going to change across the shock wave by drawing a very thin control volume, right, across the shock. All right. So first of all, let's look at what principles are we going to be using over here. So first of all, the mass is going to be conserved across the shock wave, right? So let's actually denote all the quantities on the left to be with the L. So we have density at the left, we have velocity at the left, we have pressure, and we have temperature, right? Left. And on the right we have the same thing. Okay, so first let's think about conservation of mass. Conservation of mass means the density multiplied by velocity has to equal to the density multiplied by the velocity on the right, right? So because they are equal, we usually just represent it as m dot, which is the same on both sides. Good? Okay, and then we also have, so all of these are only true, let me just remind you, when we take a frame of reference that's stationary moving with the shock wave. Okay, and if you have a frame of reference in which the shock wave is actually moving through you, this doesn't work anymore, right? Because even if you take a very thin slice, as the shock wave is moving through it, the amount of mass in the control volume actually changes, because on the left and on the right they have the air has different density, right? So if the proportion of left versus right actually changes with time, then the total amount of mass actually changes. So this is only true when you take a frame of reference that goes with the shock wave. Okay. All right. Then we have conservation of momentum, right? Again, we're taking a steady state of reference, and the momentum has two parts, right? One part is the momentum flux, and one part is the force by the pressure, right? In this case, because the pressure on the two sides are different, so the force by the pressure is going to actually do a lot of work over here. So let's say the mass flux is RL times UL squared, right? So that's how much momentum flux into the left-hand side per unit amount of time. And minus UR times rho R times UR squared, that's how much momentum goes out of the control volume per unit amount of time. There is also forces, right? So that should balance the forces. The force should be, so this is the momentum flux that goes into the control volume that should twice to increase the amount of momentum. And that should be equal to the amount of force that's acting on the control volume, right? It should be opposite. So let me actually do it at the force, and they should be 0. Okay, the force that also tries to push the flow towards the right would be equal to PL minus PR, right? That's PL is the force per unit area on the left, and PR is the force per unit area in this side on the right, right? So the momentum flux, which tries to also increase the momentum in the right direction, and the pressure, which is also tries to increase the momentum in the x direction, they should add up to 0, right? So that's momentum conservation. So we have these two equations. And another equation that is actually obviously energy conservation. But instead of writing down energy conservation, let's actually do a little bit of, actually, before we go into energy conservation, let's actually do a little bit of math on the momentum equation. So here we can write rho L times UL squared as m dot times UL, right? Okay, so because that's rho L times UL, which is m dot times another UL, minus m dot times UR, right? And plus PL minus PR equal to 0. So this equation actually reveals what the shock wave is doing, okay? Let me actually make it even more explicit. M dot times UL minus UR plus PL minus PR is equal to 0. Okay, so this makes the work of the shock wave more explicit. It is trading velocity with pressure, right? One of these is positive, one of these are negative. And somebody tell me which one is positive, which one is negative.
The velocity term is positive and the pressure term is negative.
We have a high-speed flow going to a shockwave. Just remember the car video, right? There are like cars traveling at high speed over here. It bumps into the shockwave, it stops, right? It becomes a low speed. So UL minus UR is going to be negative, right? UL is, it's going to be positive. Yeah. So sorry, you're right. So UL is fast, UR is slow. So yeah, so this is positive, and this is going to be negative. So the PL is low and PR is high, right? So think about the region of the car that's tightly packed as a high pressure region, right? The cars that are traveling freely as like a low pressure region. So as the cars bump into here, the pressure suddenly increases, and the ratio of the increase is exactly m dot. All right. So now let's actually let's try to put this equation aside a little bit, right? And think about yet another equation to consider. So this other equation is derived by a mental experiment, right? So let's actually take exactly this shock wave and think about a device to get to that shock wave from an upstream plenum with almost a zero flow, right? So let's actually move the shock wave to here, and this control volume, right? We basically move it to here, and we are going to put it into a geometry where we have 0 Mach number upstream, and afterwards so basically the contraction and expansion are so large that the Mach number far upstream and the Mach number far downstream can be thought of as negligible. All right. Okay. So now if you take a control volume and that encompasses the whole thing. So take a control volume that starts from here and ends over here, and think about the conservation of energy through the whole thing. And the assumption is we have isentropic flow both upstream and downstream. The only thing that we cannot assume is isentropic is across the shock wave, because the shock wave is so thin that you cannot neglect the amount of heat transfer and viscous fluxes from one side of the shock wave to another, right? We know that if there is a sudden pressure change, there is probably also a sudden temperature change, right? You get the air gets compressed suddenly. So when there is a sudden temperature change across a tiny region, there is going to be heat transfer, right? And as we're going to see, there is also velocity change. When you have velocity change across a small region, you have the molecules between the two different regions cross each other due to heat motions, and that transfers momentum also. So you cannot assume the shock wave is isentropic. All right, but we are assuming both upstream and downstream, we shape the geometry so that we have isentropic flow. All right, so when we do that, what happens to energy conservation? So think about the energy conservation in this case. So the conservation of energy is the flux of the summation of internal energy and kinetic energy, right? Okay, so because the and also the force, the work done by the pressure. So the flux of energy should balance the work done by the pressure upstream and downstream. Again, we cannot assume the pressure upstream and downstream are the same, right? Across the shock wave, the stagnation pressure probably has changed. So even though on both sides there is acceleration and deceleration to Mach 0, the stagnation pressure is not the same. Therefore, the pressure upstream and downstream are not the same. But when you calculate the energy flux is going to be, let me just write m dot times CV times T on the, let me just say this is, here we have T naught and here we have T exit. All right, CV times T naught. So that's the flux of internal energy into the control volume minus the same m dot, right, mass flux times CV times T exit. So that's how much the energy flux has been in balance, right? That is actually a term that tries to increase the amount of energy in the system, all right? And another thing that tries to increase the amount of energy in the system is the work done by the pressure, right? And if we have P naught upstream and the P exit downstream, the amount of work done by the pressure is actually equal to the velocity at 0. So okay, so let me just say one thing is that although the Mach number is equal to 0, the area is going to be so large that as Mach number goes smaller and smaller, the area goes larger and larger, right? So the work done by the pressure is equal to the pressure times velocity times area, which should not be going to 0 because velocity times area is not going to go to 0. Okay? That plus the P0 times U0 times A0 minus PE times UE times AE, right? That should be equal to 0. That's the work done by the pressure, right? Okay, and let's actually rewrite this term as m dot CV T0 minus CV TE, and let's rewrite this U0 as m dot divided by rho 0, and UE as m dot divided by rho E, right? What you get is right. One second. I think there is also a divide by A0. So that's the mass flux, and we are dividing by density. Yeah. So velocity times density times area is mass flux, AE. So that means the pressure force can be written as P0 times divided by rho 0, right? Again, times the mass flux. So the mass flux can be pulled out of the entire thing, minus P exit divided by rho exit. Agreed? Okay. Okay, so now the important thing to realize is that this is equal to 0, right? Okay, so the important thing to realize is that P over rho is proportional to temperature, right? P over rho is proportional to temperature. So basically we have something times the temperature at 0 plus something times temperature at 0, right? Both are constants. Minus the same thing times temperature at the exit, minus right? So what this means is that the whole parenthesis is 0 equal to m dot times CV plus P is equal to like rho RT, right? So basically CV plus R times T0 minus TE is equal to 0. So that means T0 is equal to TE, right? This is probably one of the most simple relationships you can obtain through a shock wave. That is, if you isotropically accelerate or decelerate both sides of the shock wave to Mach 0, the temperature would actually be equal. Or in other words, the stagnation temperature, right, on both sides of the shock wave does not change. So everything else is actually pretty complicated, is a function of the Mach number. The only thing not complicated is the stagnation temperature, right? Across the shock wave, the stagnation temperature does not change, right? So that means stagnation temperature is the same across a shock. All right. Okay. So this is probably the simplest statement you can learn for what happens across a shock. Okay, so now the stagnation temperature is constant. That means we can use that to simplify a lot of stuff. I don't know if we have time to do it in this lecture, but I'm going to tell you what is the logic, right? Okay, so the most important thing is basically we can plug in the stagnation temperature equal to constant a formula into this equation, right? Together with the m dot being the same across the shock wave, we can actually write everything in terms of Mach numbers. So let me actually start to write it. M dot times UL minus UR plus PL minus PR equal to 0. Or let me just write it as equal to minus of PL minus PR. Okay, so where UL is equal to the Mach number on the left times square root of gamma P over rho, but the gamma P over rho can be written as gamma R times TL, right? The temperature. And because we know that stagnation temperature is constant, we would actually like to represent everything in terms of temperature. That makes things easier. So this is equal to ml gamma R times the stagnation temperature. Let me just write as TT, right? That's the stagnation temperature. Square root, and then there is a square root of temperature effect that's we know can be represented again in terms of Mach number, and because of the square root we have 1/2 power, right? Okay, so that's because TL is equal to the total temperature times this to the minus 1/4 power, right? That's the definition of total temperature. Okay. The same thing can be said about UR. All right, okay, and so PL and PR can also be written in terms of Mach number, right? So in here, what we are going to do is the easiest thing to do is we write this is equal to minus 1 over actually, we are going to write the m dot explicitly in terms of rho L, UL, and PL minus PR, rho R, UR. And what we are going to be basically doing is that PL over rho L can be written as temperature, right? Which is going to be represented as Mach number again. This can be written as temperature, which can be expanded in terms of the total temperature times a function of Mach number. The velocity, again, can be written as the Mach number times speed of sound, and the speed of sound can also be written as temperature. So everything can be written as basically Mach number and the total temperature. And it turns out the total temperature cancels out on both sides, which means you can derive a relationship that relates the Mach number on the left and Mach number on the right. So that is turns out to be this equation we solve. So the solution of this is this, right? M1 and M2 are basically my M left and M right. So if you know M1, the Mach number on the left, you can solve for what is the Mach number on the right. Okay, so as we have seen, like everything becomes easy once you figure out the Mach number. For example, we can compute the ratio of the densities by plugging in the Mach number relation on this side, since we already know Mach 1, right? Since we already know M1, we know like what is the so basically we can figure out what is the density and what is the pressure ratios on both sides also. And when you plot this on a graph, this is what you can see, right? So on the x-axis is the Mach number before the shock is always greater than 1. And the Mach number after the shock decreases as Mach number upstream of the shock increases. And the other relationships can be also just derived using the Mach number relationship. Okay, so we'll come on Wednesday and start working on several examples of how do we use this graph to figure out real life problems. Okay, so see you Wednesday.